So in the last video, we talked about this idea of factor pairs. We said that the number 12 had three factor pairs, 3 and 4, 3 times 4, 2 times 6, 1 times 12. The number 17 had only one factor pair, so we call that a prime number. And we saw that the number 15 had two factor pairs, 1 times 15, 3 times 5. We looked at divisibility rules for 2, 3, 5, 9, and 10. I realized I left out the divisibility rule for 4 also. Is a useful one. But again, you should look at the divisibility rule videos that are attached to the document. And then we looked at 96, which was kind of cool because it had 1, 2, 3, 4, 5 interesting factors and a sixth, what I call a boring factor, the identity factor. So today we're going to look at something, and then we looked at 187, which was hard to figure out, right? We figured out that it had one interesting factor, 11 times 17, and we kind of had to play around till we got that. So what we're going to look at today is something called prime factorization, right? A prime number is a number that only has the non-interesting factor pair, right? Only one in itself. So like 17 we said was prime because we can only break it up, factor it as 1 times 17. So prime factorization means you take a number that has that is not prime. That's actually called a composite number. It's made a composite, by the way. So a composite number is a number which is not prime. And it's called composite because composite in English means to make something out of something else. So, if you're building a material that's a composite material is made up of multiple materials. Composite materials became very important doing airplane design because you can make very light composite materials, but that's not really relevant to what we're talking about. So a number like 12 is composite because it's not prime. And we saw that you could break it up into different factor pairs. Prime factorization means that you're breaking it up as far as you possibly can break it up so that there's no more breaking up that you can do. And so let's look at how that would work. So if we break 12 up, and you can pick any factor pair you want except for the boring one, which is 12 times 1, and we'll talk about why that's not useful. Let's take 3 times 4, and I'm writing it with this little arrow coming down, or these little lines coming down, to show that I'm actually breaking 12 up into 3 times 4. So 3 can't be broken up anymore. That's prime. So I'm going to highlight that because I'm done. But 4 is not prime. 4 is composite. So I can break 4 up into 2 more numbers. 4 is 2 times 2 times 2. And so let me highlight that. So the prime factorization of 12 is, and we normally write the prime numbers from least to greatest, so 2 times 2 times 3 is the prime factorization of 12. So 12, this is the most we can break 12 up. And if you notice, we can find the factor pairs because 2 times 2 is 4. If we go the other way, we get 4 times 3. But 2 times 3 is 6. 6 times 2 is also a factor pair of 12. So that's pretty useful. Let me show you why breaking it up into the non-interesting one is kind of useless, because if we said, okay, 12 is 1 times 12, 12 is 1 times 12, 12 is 1 times 12. Okay, you get the idea. This is not going to go anywhere. So that's why that's considered to be a non-interesting factorization. Let me erase that. I said let me erase that. There we go. Okay. So when we took 187, we broke it up into 11 times 17. Since 11 and 17, since these are already prime numbers, 11 times 17 is the prime factorization of 187. Can't do any better than that. 96 is sort of the interesting one. Remember, 96 is the one with all the, where is it? Oh yeah, all these factor pairs. So let's do the prime factorization of that. So 96, and you can really start with any factor pair that you want. It doesn't matter at all. So I'll just do 2 times 48. So 2 times 48, and I'm going to draw a line here. and I'm going to highlight this. So 2 is prime, can't break it up. 48, well, I happen to know that 48 is, that 48 is let's see, let's just divide it in 2, why not? So 2 times 24. Okay. Because I couldn't really remember what 48 was. It's 7 times 8, right? No, that's 56. 6 times 8, 6 times 8. Okay, see, I can't always remember this stuff. But no matter, 48 is also 2 times 24. We can keep breaking up 24, and that I know is 6 times 4. I could have done 8 times 3. I could have done 2 times 12. Doesn't really matter. I'm going to do 6 times 4 just so we can see that the 6 can now be broken up into 3 times 2, and 3 and 2 are prime, so I'm going to highlight those two. And the 4 can be broken up into 2 times 2. So we get a prime factorization. Wow, there's a lot of 2's there. So looks like 1, 2, 3, 4, 5 2's. So 2 times 2 times 2 times 2 times 2. And then there's that one little 3 hanging out here. There it is. Hey, 3 times 3. That's the prime factorization of 96. And I can get any factor pair by combining whichever ones of these I like. So let's say I can combine, actually let's just look at this again. So that's the prime factorization of 96. There's 5 2's and a 3. So I've broken up 96 as much as I possibly can break it up. And there's cool things I can do with that, which I'm not going to talk about. But let me just show you that one of the things I can do, let me highlight this in purple. If I pick, let's say I'll pick this 2, and this 2, and I'll call that one of the factors. And then on the other end, I'm left with, I'll do this in brown, this 2, and this 3. So the purples, right, 2 times 2 times 2, that's 8. And the browns, 2 times 2 times 3 is 12. That's a factor pair. 8 times 12 is 96. So hopefully you can get some sort of idea, let me erase these, about how breaking up a number into factor pairs can be used the prime factorization can be useful to find factor pairs. And this could be useful if you were trying to simplify fractions or add fractions or anything like that, where you need to use the factors to do that.